So we'll now focus our attention on some special probability distribution functions. These are some of the commonly used or commonly encountered distributions in physics and or statistics. So we'll start first with discrete distributions. So first we should introduce a concept known as Bernoulli trials. So Bernoulli trial is an experiment with two possible outcomes. So an example would be the tossing of a coin. Let's say we denote the outcome of the experiment by a random variable k, and corresponding to the success or the failure, k is either 1 or 0, and this happens with, let's say the success happens with probability p and the failure happens with probability q, which is nothing but 1 minus p. So the probability distribution function in this case, PDF, so it basically denotes the number of times we encounter a success times the number of times we encounter a failure when this is done multiple times. Now with this probability distribution function, we can compute the moments and central moments. So expectation of k to the power m is nothing but 1 times p 0 times 1 minus p, which gives you p. And if you look at the central moment, it is the moment about the mean. In this case we get since there are only two possibilities in this discrete scenario, you obtain so k minus mu, so that occurs with a probability of p, and 0 minus p, that occurs with a probability of 1 minus p. In particular, we can see that e of just k to the power 1, setting m equals to 1, which will give us the mean, is just p. And if we are interested in the variance, which is expectation of k square minus the square of the expectation of k, and that is simply given by p times 1 minus p, or p times q. This can be verified by using the definitions from above. Okay. Now this brings us to the first distribution that we want to discuss, which is known as the binomial distribution. So the binomial distribution gives the probability of k successes in n independent Bernoulli trials. In each trial, having a probability P of success. So this is normally denoted by it's capital B. K is my random variable and N and P are the parameters associated with the distribution function. Now the probability of K successes followed by N minus K failures can be denoted by this product P to the power K, Q to the power N minus K. But we must keep in mind that these can occur in different orders. That's why we have to include this combinatoric factor for taking into account the different permutations, basically. Now the binomial distribution, so again this is left as an exercise to the student to verify that the binomial distribution has the following properties. The mean is given by n times p. The variance is given by n times p times 1 minus p, or n times pq. Skewness, using the formula defined in an earlier lecture, can also be expressed as a function of p and n. And similarly, kurtosis and lastly we can also define the characteristic function. As an illustration, we can look at how we prove the first of these. So the mean is the expectation of k. So for the discrete case, this is given as the sum over k times the probability distribution function. So we can take the pieces which are not exactly dependent on k outside. I've basically taken a power of p and a power of n on the outside. So now the summation starts from k equal to 1, and the k factorial in the denominator can be split into k times k minus 1 factorial. So we can cancel this out from the numerator and the denominator, and we define a new n and k. So let's define n prime as n minus 1 and k prime as k minus 1. So that allows us to again start the sum from k prime equal to 0 all the way up to n prime. And numerator we get n prime factorial, k prime factorial. N minus k is equal to n prime minus k prime because both have an equal shift. So now if you notice, this is nothing but the probability distribution function itself. So just with k prime and n prime instead of k and n as before. So this sum should basically give 1. Or the other way to look at it is this sum is nothing but the binomial expansion p plus 1 minus p whole to power n prime, and that is 1. So basically the mean comes out to be n times p. Now many distributions have what is known as a reproductive property. That is, the probability distribution function of the sum of 2 or more independent random variables, each distributed according to the same PDF, is the same PDF as for the individual random variables, although with different parameters. So let's say x and y are two independent random variables, and both are distributed according to a binomial PDF with parameter p. So we can write since they are independent, we can write the joint PDF as a product of their individual PDFs. Then the question becomes, what is the probability distribution function for x plus y? So we'll do a change of variable and introduce some new parameters. So the new variables are z1, which is x plus y, and z2, which is just y. So which will imply an inverse transformation of x equal to z1 minus z2, y equals to z2. And we introduce new parameters. nz1 is nx plus ny, and nz2 is ny. So we've seen before, when we do a transformation of variables or discrete PDFs, new PDF and the old PDF just display an equality without any Jacobian. So the new PDF, in terms of the new variables, let's say we denote it by g, z1, z2, is simply f of z1 minus z2, comma z2. So now we already have an expression for f in terms of x and y. We just have to substitute for x in terms of z1 minus z2 and for y in terms of z2. So that basically gives us and for the second case, we are just replacing ny by nz2, y by z2. So from this, so this is the joint PDF for z1 and z2. So if we want to compute the probability distribution function for z1, which is just x plus y, then that is a marginal PDF of this joint PDF. So what is basically needed is that we sum over z2. So g1 z1 is sum over z2 of g z1 z2. Now this can be written as we use the symbol for the number of combinations. So basically NCR is nothing but n factorial by r factorial and minus r factorial. For normalization, the sum over Z2 should basically give us in Z1 C Z1. So ultimately this shows that G1 is also a binomial PDF. We can write G1 of x plus y is a binomial with new parameters x plus y and nx plus ny. Thus we see the reproductive property reflected here in the sum of the two random variables that follow a binomial distribution. Now, one straightforward generalization of the binomial distribution is the multinomial distribution. So this basically corresponds to the case where we have more than two outcomes. So let's say we have m different outcomes with probabilities pi. So we'll consider, let's say, n experiments and ki is the number of experiments with outcome I. Then the probability distribution function is given basically by a generalization of what we had for the binomial case. This multinomial with respect to the parameters k1, k2 to km, or more appropriately the random variables k1, k2 up to km, and the probabilities p1, p2, pm, n being the total number of experiments. This basically assumes this form: n factorial by k1 factorial, k2 factorial, product of all these factorials, and multiplied by p1 to the power k1, p2 to the power k2, all the way up to pm to the power km. And this is subject to the conditions that if we sum over all the probabilities, it should give 1. So sum over the pi, where I goes from 1 to m, and sum over all the numbers of the different outcomes, the number of times we receive different outputs, that should total the total number of times the experiment is conducted. So sum over ki, where again I goes from 1 to m, should give me n. Now, a more condensed form in which the multinomial PDF can be written is, let's say we define a k vector and a p vector, and we write this as we use the product sign to simplify it and write a general term there. Now, to calculate expectation values, we make use of the binomial PDF. Basically, if we are considering, let's say, a histogram which has m bins, so let's say we draw a histogram. Each of the bins basically specify a range of values within which a result could fall, and the y-axis basically gives you the number of occurrences of that particular outcome. So histogram is a good way to study probability discrete distributions and see what kind of frequencies we are encountering for different outcomes. So let's say we are considering a histogram of m bins, and the probability is pi that the outcome will lie in the ith bin. So for n experiments, the probability that number of entries in the bins will be given by ki. These ki is given by the multinomial PDF. Now, to calculate expectation values, we'll utilize binomial PDF. For a given bin, the outcome is either an outcome is in it with probability pi or not. These probabilities pi and 1 minus pi. Now take note of the fact at this time 1 minus pi appears as a sum over all the other p's. So now with this assignment of pi and 1 minus pi, we have simple case of a binomial PDF, or in other words, the marginal PDF of the multinomial is the binomial. So we can borrow the formulas or the results from the binomial case. We know that in that case, the mean is simply given by n times the probability p, and the standard deviation is simply given by, or the variance to be appropriate is given by product of p and 1 minus p. From this we can also calculate the covariance. Which basically turns out to be minus npi pj I not equal to j. And lastly, this leads us to the correlation coefficient. Which can again be written in terms of the PIs and PJs. The correlation comes about because n is fixed, sum over the ki's is n. Therefore, the ki's are not independent. But if n is not fixed, That is, if n is itself a random variable, then the bin contents are not correlated. But in such a case, we do not have a multinomial PDF. What we have is a Poisson probability distribution function, something which we will discuss next.